Batteries contain one or more electrochemical cells. They use the energy from a chemical reaction to generate electrical energy. Batteries consist of at least one anode and at least one cathode.
To demonstrate that a voltaic cell will generate an electric current, we have a flash bulb attached to a piece of copper wire and a piece of magnesium ribbon. We're going to lower these into hydrochloric acid. First the copper wire and then the magnesium ribbon. An electric current will be generated which will ignite the bulb. To demonstrate the copper-silver oxidation-reduction reaction, we're going to place a piece of copper wire in a petri dish and add silver nitrate solution to it. Here we can see the silver crystals beginning to grow, causing the copper wire to look gray and fuzzy. The copper wire you see under the microscope appears slightly out of focus, but as the silver crystals begin to grow and grow towards your eye, they will sharpen and become in focus. As the growth process continues, you begin to see the bright metallic crystals of silver metal. Here we see the contrast of the original copper wire to the wire after it has been in the silver nitrate solution. You'll also notice that the solution has turned from clear to pale blue. The copper metal has become the copper 2+ ion in solution, resulting in the blue color. The silver ion solution has become crystals of silver metal.
The reaction of silver with sulfur to form silver tarnish is an oxidation-reduction reaction. When silver atoms come into contact with sulfur atoms, electrons move from silver atoms to sulfur atoms. Each silver atom is oxidized when it loses one electron to become a silver 1+ ion. Each sulfur atom is reduced when it gains 2 electrons to become a sulfur 2- ion. In order for silver to lose electrons, sulfur must gain electrons, making the processes of oxidation and reduction interrelated reactions.
Everyone appreciates the shine of chrome, but chromium ore is not overly abundant and therefore expensive. Also, pure chromium is a brittle metal that is hard to work with. How then can just about anyone afford beautiful chrome accessories? This is accomplished by the deposition of chromium ions onto a base metal using electrolysis in a process called chromium electroplating. The preparation of the base metal is essential for quality plating. The base metal must first be cleaned to remove both grease and oxidation. Often the metal is then chemically etched to improve adhesion of chromium ions. In the electrolysis unit, the base metal is used as the cathode, and a lead bar immersed into chromium solution is used as the anode. As direct current flows, chromium metal is deposited onto the base metal. When the desired depth of plating has been reached, only a final rinse and polish is needed. Even a thin layer of chromium provides the beautiful, lustrous finish. Objects subjected to greater wear need thicker layers of chromium. As an added benefit, the chromium provides a protective layer for the base metal beneath.
To demonstrate the electrolysis of potassium iodide, we have a potassium iodide solution which we'll place in the Petri dish. We'll then add a few drops of phenolphthalein indicator to the potassium iodide solution. We've connected two pieces of carbon pencil lead to serve as electrodes to a variable power supply. We're going to place those into the solution. The bubbling is occurring at the cathode as hydrogen is produced, and the solution around the cathode is turning pink as the hydroxide is generated in the presence of phenolphthalein. The solution around the anode is turning the yellow-brown as I2 is generated and combines with the I- ion to form I3-, which is brown in color.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution, and the cathode is a copper bar placed into a copper-2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching a voltmeter to the cell shows that electrons flow from zinc to copper. The voltmeter reads 1.103 volts. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.